accessible to spintronic applications in future. And I think this might be the connection, although I'm not very much talking about any NMR or EPR results today. I think the spintronics or potential spintronics application might be a good connection to the research life of Konstantin. So first I have given the title of my talk here is the anisotropy of the 4F states in 3D 4F Metallacrown complexes. And I will basically come to this only at the end of my talk, and I will show you why this is so. So I would like to acknowledge people having contributed to this talk. So of course, there are my co-workers in the lab and the chemistry lab and the University of Mainz. And I also mentioned here a few of them being particularly involved in this work here. And yeah, chemistry would be sometimes boring if there was not the nice physics behind the spin physics. And the spin physics we basically do with my dear colleague Hans-Joachim Elmers from the physics department here at the university, but also due to a collaborative research center with the group of Christiane Ziegler at the TU Kaiserslautern. I also will show you very briefly some results from other groups. So I would like to mention especially the team of the Helmholtz Zentrum in Berlin, where we did all the synchrotron measurements. Okay, so the motivation, as I said, is I'm trying really to go for spintronics applications. So in the field of all this magnetoelectronics, what we deal or what we have to address is the injection and the manipulating and as well the detection of the spins. And usually this is done in the solid state environment. And what is familiar probably to all of you is, this is a very pictorial view of a spin wall for a magnetic tunnel junction. So which terminology is correct depends on whether you have it's a spacer between two ferromagnetic layers, whether you have a semiconducting or an insulating spacer. So this is like it's composed. So usually you have a ferromagnetic layer, which is called a spin injector, and we have a spin detector, which is also a ferromagnetic layer. On top and in between is the spacer. And as long as we have a spin, as long as we have a spin that is polarized by the spin injector, it passes very quickly through the spacer and arrives to the spin detector once that the magnetic moments of the ferromagnetic layers are aligned parallel. Then we have, of course, a very short, a very small resistance that we measure. And of course, as I said, we have two ferromagnetic electrons, and one of the prerequisites to use this is that we have two ferromagnetic layers that have different coercive field. And this is important in order to allow the system, at least for one of these ferromagnetic layers, to change position, to change direction of the magnetization. So by sweeping it with an external field, we need to have another orientation of one of the ferromagnetic layers, and this is visualized here. In this case, now we have an antiparallel alignment of the moments of the ferromagnetic layers, and this has a consequence that now the spins are scattered either, or they at least do not arrive to the spin detecting layer, and this means we have a high resistance. This is a very, very simplified picture, and of course, in reality, it looks more like this. So I took this from a paper from Jingji, quite old one, but it shows very, very nicely how it's composed. So we have on the left-hand side on the top, we see that we have two ferromagnetic layers. The one is the lanthanide strontium manganate, abbreviated as LSMO. And on the very top, we have a cobalt ferromagnetic layer, which is supported on an aluminum layer. And in between, we have a spacer. This is shown on the bottom. We have the ferromagnetic, we have the organic layer, and then we have the ferromagnetic layer. the second ferromagnetic layer. And if you switch now the magnetic field, you see then that we have a difference in the resistance. So we have either, if this is a parallel alignment of the layer, we have low resistance, and if we have a anti-parallel alignment, then we see that we have a different magnetic resistance. So this is the motivation behind. So this is done how it's done classical. In a classical spin world, we have, as I showed you, inorganic semiconductors, which are easily accessible. This is a big advantage, but they have a disadvantage, and this is that they're composed usually of heavy elements. And those heavy elements show strong spin orbit couplings, and so a pronounced spin scattering and is real, and spin relaxation times become small. In contrast to this, and this is why molecular spintronics came to be of interest several years ago, is that molecules may show exceptionally long spin relaxation times, and so they show pronounced as well quantum effects that might be of interest. And when the physics are talking about organic spintronics, they assume that they have what we chemists call really an organic material. So a material which is a large device, which is easily accessible. But for a chemist like coordination chemistry, like we are here tonight, we have a problem with this organic spintronics, and this is simply because we do not understand exactly how they are to be built in order to have a really accurate characterization of the microstates, because they are extended systems. And here come the single molecule into the game. In single molecule spintronics, we use really single molecules, and so are accessible to measurements that are intrinsically local. So what we can do is that we can easily relate now geometry and the electronic structure. And so for what we think as a chemist is very, very appealing for us is that up on building molecules with showing strong exchange interactions, we can convert the spin information into molecular orbital information. And this is what we are used to do as a coordination chemist. Of course, if we would like to deal with the exchange interaction, we have to deal with the Heisenberg exchange model, which usually accounts for the distance of the spins and the orbitals that are involved, but this might not be enough. So what we need to do is we have to extend the Heisenberg exchange interaction and really to add a term which takes account the anisotropy of the system. So this is of very crucial importance, and I will show you in a moment why this is the case. So we would like to study an anisotropic system. Then we, as a very easiest way, we go for a system which is a magnetic surface. On top, we put a molecule, and the molecule should be as simple as possible. So we take a molecule that has a simple electron hole or a simple electron, and is composed or is flat. So it sits really very good to the surface and can exchange couple. So we did this some years ago. So we used a derivative of porphyrin, and which we decorated with bulky steric groups in the periphery, so we could make sure that we don't have a stacking of the molecules themselves on a surface, but they are very well separated. And we did a UHV deposition on an iron oxide surface, and then we investigated how this molecule behaves. And so we could do STM, so we could get an idea of the measurement. We did even STS measurements, so we could look for the local density states mapping. And all of these measurements really confirm very, very nicely that we have a flat orientation of the molecule on the surface. And already the STS measurement indicated us by that time that we have an interaction of the copper center with the magnetic surface. So to get better insight in the exchange interaction, we had to apply a surface sensitive technique, and at least a technique which is sensitive to the anisotropy of our system. So of course, EPR in this case is not possible because on a substrate is not very feasible in this case. So what we did is we went to the synchrotron and did some X-ray absorption measurements and also XMCD spectra experiments in order really to get a very, very good information on the chemical environment and even more on the magnetic states that we are interested. Now I'm going very briefly through these experiments as they will be of importance throughout my talk. So the X-ray absorption spectroscopy, we measured by that time at only 20 K. Nowadays we are at much lower temperatures doing, and we did just very, very quickly. We just did several experiments. So we had the powder that we deposited on the substrate, as well as we prepared some monolayers. And for the monolayers, we then applied different orientation. We could realize different orientations of the substrate with the molecule sitting flat on the surface in relative geometry to the magnetic field and to the incident beam. And so we could get a really three-dimensional idea of our molecules, at least in some extent. And so we could prove by this X-ray absorption spectroscopy already that we have a flat orientation of the molecule on the surface. So we were fine with this. And then we applied the XMCD spectroscopy. And XMCD spectroscopy, to all of you who are not very familiar with this, is a very nice technique if you would like really to get to know more precise information about your electron hole, about your D shell that you're interested in. And if you would like to see the D shell, or in our case, the hole in our D shell, so we have a D9 system, so we have if you have a flat molecule or a flat coordination sphere in the copper, what we see is usually that we have a dx square minus y square orbital is only singly occupied. So this is our hole in which we now can absorb, which can absorb now a photo electron from a lower state. And so if you would like really to get to know more precise information about this, what we have to do is we have to make this absorption, the X-ray absorption, spin dependent. And this is done very nicely by the circular polarized magnetic dichroism. So what you do is that you take a circular polarized photon, and that is not a photon, it's a high energy photon, of course. And so by doing so, you transfer the angular momentum that you impose on this photon to the low-lying core levels. And if you have core levels, like in our case, we have the P levels that have different spin orbit coupling. So we have a L plus S coupling and an L minus S coupling. So we have different spin orbit levels in this case. We see that we have different transition probabilities depending on whether we have a right polarized incident beam or a left polarized incident beam. And we transfer our angular momentum to the photon that is now absorbed by our hole in the D shell. So if you would like to say this is the valence band, like the physicists see their systems, of course, this corresponds exactly to the LUMO, to the SOMO in our case of our molecule. So this is the electron hole where we are hopping into. And so due to this very different transition probabilities, what we have that is that we can, that we can very exactly do a different, I'm going back, sorry, that we can do a differentiation in our absorption spectra. So we see here that we have different absorption intensities for left-handed circular polarized light and for the right and for the left one. And if we do so, we see here, this is an X-ray absorption. And of course, if we do here if you subtract the one from the other, we see that we have here residing, and this is called the XMCD signal. And we can do this very nicely, and we can even integrate this. And due to a very simplified mathematics behind or physics behind, we can, taking some assumptions, we can apply a sum rule analysis, and the sum rule analysis allows us to deviate or to distinguish between the magnetic moment for the spin and from the orbital contribution. And this is a very nice measure, really, to give us an idea how strong is the spin contribution and how strong is the orbital contribution. In our case, of course, the orbital contribution is vanishingly small, and all we were interested to see was the spin contribution, but in all these different measurement arrangements that I showed you before. So at the final end, what we could really extract from all this experiment and put this in a nutshell is that we had, of course, a very strong exchange interaction arising between the single spin of our copper system shown here and the magnetic moment that we applied for the iron oxide surface. So if we had the magnetization of the surface being orthogonal to the magnetic surface, then we observed a higher magnetic moment for the copper moment than we would expect theoretically, while in the opposite case, if we aligned the magnetization of the substrate parallel to the surface, then we observed a much lower magnetic moment for the copper ion. So we have really very strong, if not this a hybridization, at least we have a very strong anisotropic interaction. This was what was to prove. And of course, this is very nice. And I'm now going for a very brief moment to a kind of an iconography of this, what I have shown you before. So we have a single molecule and we have a substrate. And of course, we're interested to see what is going to happen if we put them together. And if we do so, of course, what we have to take into account is that the single molecule, we have to consider that we have spin-spin interaction, we have spin-orbit interaction, we have an anisotropy that we have to take into account. And the same holds for the substrate. Also here we have spin-spin, we spin-orbit, and phonon interactions that we have to take into account. So it's going to be a little bit more complicated if you would like simply to study the interaction. We have a manifold of parameters that we have to take into account. And of course, in an ideal case, as I showed before, we even are able to get a hybrid material, and then things become really very complicated. Okay, and finally, what we would like to see is if not only if it's complicated, we would like to understand the spin phenomena, and then we would like to understand how we can trigger them externally. So this is the ultimate goal. Of course, in between to the ultimate goal, we have to put some milestones. And the very first milestones we put here is that we would like to have a molecule which has huge energy barrier. So in either case, a single molecule magnet that we put on the surface. And then of course, we have to understand the coupling, the exchange coupling of the molecules with the ferromagnetic surface. So these are our milestones. So far, so good. So I've shown you that we understand quite nicely the spin per molecule, one spin per molecule on the surface, we understand. But things are getting more complicated once that we are turning to have more than one spin. Then we have not only to take into account that the spin does interact with the surface moment, but also that we have probably exchange interaction in the molecule itself. And so if you would like to study this, we have robust molecules. So we have to have, and this is one of the major requisites and one of the major drawbacks in all this molecular spintronics community, that very often the molecules are not robust enough, or if they are at least thermodynamically robust enough to put them in ultra high vacuum conditions on the surface, then they very often are not redox inactive. So in our case, we put here, and we were successful to put a manifold of copper centers in a so-called Metallacrown, which I'm going to show you in a moment, on a gold 111 surface, and could show that they are aligned very, very nicely on the surface in a two-dimensional sheet. So these are these metallacrowns I was referring to. So we call them simply because they have the shape more or less of a crown. So this is why they are metallacrowns. Now, this is not basically true. To be very honest, it dates back to the research of Vincent Pecoraro, who in the year 1989 already reported the first metallacrown composed of metal ions coordinated by a very simple ligand. This is salicyl hydroxamic ligand, and then very nice sulfur assembly. This forms this ring systems, and so it's coordinating here the metal ions and then forming this ring systems. And it's called metallacrown. As you see here, it's composed of units of M and O units in this case, and they are very similar to the usual crown ethers organic chemists are all familiar with. And as crown ethers themselves are very keen to have a guest ion in the center, also metallacrowns do embed a guest ion, if not in all cases, but if you do appropriate chemistry. And this is the crown ether, and substituting here now the ethylene bridges by this NM units, it was the idea of Vincent Pecoraro to call them metallacrowns, and as such they have found their way in the literature. So when we came to be interested in this metallacrowns, there was already a very nice report by Vincent Pecoraro really showing that they have very unique features, these metallacrowns. Most importantly for us, they are reliable in their formation and they're stable in solution. And they have, to some extent at least, ion pair selectivity. So our goal was by the time to apply them for the magnetochemistry, so really put them in the magnetic community, introduce them in the magnetic community. So what we did is then coming from a one spin center, as I showed you before, one spin molecule, we tried, okay, let's check in detail the metallacrown composed of 5 copper ions, shown here on the right. And all of these copper ions are paramagnetic, so we have now 5 spin center. And we were quite disillusioned to see that, wow, it's behaving exactly like a one effective spin system. And we could prove this not only by magnetometry, but also by high field EPR, which really confirmed very, very nicely that S equal 1/2 spin ground state throughout the whole molecule. And this is easily understood if you take into account, or if you consider that we have a very strong exchange interaction along this rim here. So we don't see them in the ground state. So in the ground state, what we see is just this single ion here in the center. Okay, so this is not really a high spin molecule, so we have to have another idea. And we had the idea to go for heterometallic systems. For now, it's still one of the it's the only example that I'm aware of where we have a 3D heterometallic system for metallacrowns. And so what we did is we kept the copper in the center and we substituted the peripheral ion for iron, for iron 3 ions in this case. So what we did is we had the idea, if you have a center spin, which is really having a very strong exchange interaction towards the periphery, then all the iron ions should align, all the iron spins should align parallel, and this should give rise to a very high spin state. And so of course we confirmed this by magnetometry that we have a high spin state, but coming from spectroscopy, we tried of course to have also here a local probe. EPR spectroscopy did not help us, even not the high field, because we could not get the resolution that we needed for. So the tensors were not good to resolve. And so what we did by the time is, okay, we remembered, okay, we have the XMCD spectroscopy and we did XMCD spectroscopy with the same molecule. So I showed you before how it works. So coming conclusion immediately. So what you see already is a element-specific method. So you can have the spectrum for the iron as well as for the copper in a separate way. And of course, then what we see already that here's the copper spectrum I showed you before, very similar. And that you see that the iron seems to have the opposite deviation. So where we have here on the L3 edge, we have a positive signal for the eccentricity, we have here a negative and vice versa. So this gives you already the indication that here the magnetic moments are aligned anti-parallel. This is nice. And of course, by applying the same sum rule analysis I showed you before, what we can get is the number that we have for the magnetic moment. These are relative numbers, and all I would like to show you here is that we understand nicely. Of course, we have a certain amount for the central copper ion, and we have a certain quotation of the spin moments for the iron 3 in the periphery. Of course, we have here a very, very low orbital momentum as we expect. So this is not a single molecule magnet as you can imagine. So nevertheless, we could say, okay, the high spin we can have, but now we have to watch out, can we put them on the surface, as this was our goal to go for. So we were interested to put them on the magnetic surface. As I showed you before, we succeeded on the gold surfaces with the copper. This is the copper 5 system. This is applicable for the UHV technique. So you can deposit this on a gold surface and do whatever you want to. And, but this is not true for all of our systems. This is especially not true for the heterometallic systems, or whenever you have systems that are highly charged. Then they really sit in your vessel in the UHV chamber and simply burn before they go to the vacuum phase and deposit somewhere else. So this is a bit frustrating. So you're producing a lot of coal, which is a very expensive method. So what we have to do is here in this case, and what we applied for is trying to do electrospray deposition. And this is a self-made instrument in the Technical University of Kaiserslautern, where they could really do this under very high vacuum conditions. Of course, at the beginning you have ambient condition, but at the final end you have your substrate and your molecules deposited on in a very low millibar regime. So this is how it works. So it simply has that the molecule, that the solvent molecules that you have at the beginning really fly off, and at the end you arrive to the substrate or position of your interested magnetic molecules. That is done. That it works, we could prove by mass spectrometry, but this is just to give you an idea that we could prove that it's an integer molecule that we deposit. We could also do some STM on the copper 100 surface, and you see it seems to be a bit more random because it's simply a very, very low concentration that we put here on the surface. But if you check carefully, you see it's an alignment, and it's a regular alignment. We have only one absorption geometry on the surface. So this is the good take-home message from this slide. And of course, where we have the STM, and we are lucky enough, we can have also the STS measurement. So again, density map of the spin density. And we can see that we have some spin interactions between the electrons of the molecular atoms and the metallic substrate already from this picture. And this is confirmed as we see a small Kondo resonance. Of course, this is a very small one, but this is due to the fact that we basically have just one copper center, which should really be taken into account. So this gives us an idea that we have a flat molecule, and it shows some hybridization with the surface, although it's the copper 00 surface only. So very nice. Now we had molecules that did not show any single molecule magnet behavior, so we have to think strongly also about the anisotropy of our molecules themselves, and we very successfully could embed here in cobalt-3 scaffold, cobalt-2 ions. So we could get single molecule magnets that are very, very nicely showing a prominent negative zero field splitting, and they really behave very nicely as single molecule magnets. But today I'm going to talk only about the systems where we try to embed here lanthanide ions, which are even stronger anisotropy in their magnetization. So this is the idea. And as you can imagine, going back to this slide, if you can imagine if we embed here a 3D metal ion, this might be accessible to this cavity, but a lanthanide ion is much, much bigger, so you can immediately imagine this won't fit into the cavity, and in fact what is formed is a sandwich compound. This resembles very strongly the phthalocyanine complex as reported earlier also in this conference, and of course the pioneers here by Ishikawa showing this very, very nice single ion magnet behavior, the terbium phthalocyanide compound. So this is the very similar picture here. Rather than having here phthalocyanide, we have here a metallacrown, so composed of potentially paramagnetic ions. And of course, we are now interested in the magnetic moment of the metals and how it's influenced by its surrounding. And by checking for the dysprosium, we already were very, very successful and could show that we have here a high magnetic anisotropy, leading really to a high energy barrier of the magnetization reversal. But I'm going to show you a little bit more in detail why the terbium was always the winner in the phthalocyanine sandwich complexes. And this is important also for our system here. So this is the very first report by Ishikawa from the year 2003. And the idea was behind, okay, this is the molecule. And of course, terbium has a very huge energy gap between the ground and the first excited state. And it's now a accepted idea in literature, going back to the idea of Reinhardt and Jeff Long, that we have that this goes to the anisotropy of the electron density of the lanthanide ions. And for terbium, we have kind of a flattened electron density in the ground state, while we have an elongated density in the first excited state. And this is due to the shift in the gravipolar moment. And if this is true, then we have with the embedding of this flat electron density in between the Brett-Burger parts of the sandwich, then of course, then the electron density and the electron density of the lanthanide have an idle repulsion, while in the first excited state, where we have to go through, the electron density repulsion is much stronger, and this increases the effective. So this is the idea, and if this is true, then this should be the same for our copper system, or for our nickel system, where we have the Brett of our burger being a metallacrown. And in fact, also for the terbium, we can see an out of phase signal in zero field and a more pronounced one in non-zero field. And we can extract from this that we have here at the final end really even higher anisotropy barrier. So we have even here an anisotropy barrier of 550 K. This is so far that we are aware of the highest one reported for a metallacrown in this context. So what about now the lanthanide? This is the idea of what we are interested in behind, to check for the local F states. And again, XMCD spectroscopy is a very good technique to get information. And the difference between the 3D metal ions and the 4F metal ions is that we have to take into account that for the 4F, we have a very, very huge spin dipole asymmetry. So we have to take into account that we have really here a tensor that we have to take into account additionally. But for the rest is, of course, we have to take into account that we have localized 4F states. So we have, and we have only very little deviation, or we have very little influence of our ligands or surrounding is supposed to be, and we will see if this is the case. So what we did is here that we did the XMCD spectrum for this terbium nickel sandwich complex, and the terbium complex, the terbium itself showed the spectrum down here where you see that you have the absorption from the M5 and from the M4 core level. And this is the spin and the orbital contribution. You already see that you have a very, very pronounced orbital contribution in this case. Okay, but then we were puzzled that we got also a nickel contribution, and this we were not expecting. So from the crystal structure and also from the first magnetic moment, we did not see any magnetic moment, and from the crystal structure, we did not expect magnetic moments, as the nickel 2 ions D8 systems are in a square planar configuration, so they should be diamagnetic. But of course, checking in with more care, we saw, oh, well, there is some, at least one nickel ion, which is coordinated additionally by a morpholine. So this is probably taking, or this is probably responsible for the magnetic moment that we see for the nickel. So we investigated this in more detail. And just to put this in a nutshell, what we could see is that we can strip off this morpholine, the solvent, and then we don't see any nickel contribution in the XMCD, or only very, very little. While this is not the case if we have coordinating solvents, like in this case, we tried with methanol, which is a potentially coordinating solvent. And in this case, if we did not try the sample too much, we see that we have a pronounced nickel contribution. So of course we have to take this into account just to make sure. So this is what we have. If you have a spin switching between the two states with co-ligands that coordinate or without co-ligands that coordinate, this is the picture behind. So in a square planar coordination, we have a diamagnetic nickel 2, whereas in 5 coordinated, we have a paramagnetic nickel 2, which then gives rise to this magnetic moment. Okay. So what we could not do so far by the time, because we simply did not know how to do exactly, was what I'm going to show you in the next couple of minutes. And now I'm finally coming to the anisotropy of the systems and to the title of my talk, so to speak, but it will take only very short time. So this is what we have, that we have now enlarged the scaffold in order to allow the nickel to be embedded in the center. And then we get a wheel-shaped Metallacrown. So what we abbreviate here is that we have a lanthanide 3 in a nickel 5 Metallacrown. Okay, so far this is how it looks like if you have the nickel, if you have the lanthanide in the center. So it's a very nice and beautiful molecule. And according to the picture I showed you before, now the situation should be reversed, should be at least opposite somehow. So we expect that we have here for if you take, for example, the samarium, this would be a perfect lanthanide ion to be embedded in this cyclic scaffold, as this is showing in the ground state at least a oblate electron distribution, while it in the first excited states, probably it's going to be a little bit uncomfortable for the electron density to sit here. So you will increase here the mu effective value by this way. And of course, as we had the samarium in mind, we prepared also the samarium compound, but we had also access to the terbium and the nickel dysprosium. And the terbium and nickel dysprosium already showed from the very simple KMT data that we almost have no contribution from the nickel ions, and this is simply because they're strongly exchange interacted. So this they show antiferromagnetic exchange interaction. So our moments basically arise only from the lanthanide. And of course, we do so for the magnetic moments in dependence of the magnetic field. And surprisingly for the samarium, it also shows a very paramagnetic behavior. And this was a bit puzzling to us. So we went again to the XMCD spectroscopy to get a more detailed information. And now what I'm going to show you is that we have here, if we would like really the, if you would like really to compare all this data, we have to check for how many electrons we have, what is our expectation of the spin, and of course, what is our expectation of the orbital contribution. And if we do so, we can do this for the terbium, for the dysprosium, and for the samarium. And what we see is that in overall, the resulting magnetic moment that we should observe should be approximately adding up to 9, because they are parallel aligned for the terbium, should be 10 for the dysprosium as they are parallel aligned, but they should be neglecting or annihilating each other because they are anti-parallel oriented for the samarium. And this already gives you an idea why the samarium in this case is not showing a higher strong magnetic moment. So we did not extensively investigate this further, although we did a little. But the second take-home message is that for the nickel, as it's expected, we have only a very negligible anisotropy. So the T-set operator, the dipole operator, should be is not of importance. So what we see from the experiment, if you check here carefully, you see that well, this is not adding up to 9, and this is not adding up to even 10. So what we see is that the measurement of our molecules or of our moments is a factor 2, approximately too small. And this is how we explain. And now the anisotropy comes into the game. So if it's the factor 2, we have to take into account that we have a strong magnetic anisotropy, and this strong magnetic anisotropy forces now the orbital magnetic moment along the molecular symmetry axis. So what I'm showing here is 2 pictures of the same molecule, and that has a normal to the molecular plane, and because this is the molecular symmetry axis, this is the very same shown here on the right. And in one case, so in both cases, we have also here the very same arrow here in green shown. So this symbolizes the external magnetic field. What differs now for the left picture to the right picture is this bluish arrow here. And this is simply because we assume here 2 different borderlines. So in one case, we have an easy access symmetry, an easy access magnetization. So this forces, if you have a very strong anisotropy, this might force the resulting orbital momentum and the spin momentum to be almost aligned to the molecular symmetry axis. If in the other case, we would have an easy plane anisotropy, the easy axis somehow lies in the plane area, then this would align the orbital and the spin moments to be more parallel to this. And so, of course, as we have a very strong spin-orbit coupling, we can assume that they are both aligned to each other. So this makes life for us a bit more easy. What we then have to take into account that we have to minimize the free enthalpy. And the free enthalpy, we have to take into account if we can take into account if we consider something like an anisotropy constant, if you would like to say. So if you have this anisotropy constant, we can assign the magnetic moment of the Earth moment in the following. So we have, if you have an easy axis symmetry, again on the left, and the easy plane symmetry on the right, we have the following picture that we expect. So if we have a ratio of the anisotropy constant and the magnetic moment of the Earth element, and this is approximately going to be 0, then we have a vanishing anisotropy. And what we expect is the full ionic value calculated as before. So for the terbium, it should be around 10, and for the dysprosium, it should be around 9. So this is something which we expect for vanishing anisotropy. And here, what is put here on the left, on the y-axis, is simply the projected and the ionic value ratio. So this should be 1. In contrast, if you have a large magnetic anisotropy, then what we observe, or what we expect here from this picture, is that then the measured magnetic moment is approximately half of the expected ones. And this is exactly what we observe. So what we did here is we analyzed our experiments in this frame. And then we can say, okay, what we get out from this after taking into account all this molecular orientations, and we have to put here the powder. I have to forgotten to say, we have put here the powder, measured the powder. So we assume a random orientation. And with this random orientation, of course, we have to do all these integrations here on all the sphere. And so this is important why here you have this integrals showing up. But nevertheless, the rare Earth moment that is projected on the field direction is averaged. And then we can consider taking this correction factor. And by taking this correction factor, what we obtain is surprisingly that we have the spin that we observe, and the spin that we calculate with this correction factor is 6 for the dysprosium, so only a little higher, and it's also 6.2 for the terbium, so it exactly matches the one that you're expecting for from the the half of the ionic value. So this is very, very nice, and we could show that the anisotropy here is really very, very important for the lanthanoid ions. So for the physicists among you, I don't know who is interested, we could even calculate for the dysprosium and the terbium the magnetic anisotropy energy, but I wouldn't like to go into detail. The very last slide that I would like to share with you is that, of course, we were so excited to do this anisotropy, or this angular dependence investigations for a powder, which is an average, of course, that we said, okay, we have to do a very, very huge single crystal. And we did so, and we went to the synchrotron, and we did some angular dependent measurements on the single crystal. Of course, then you cannot use the total electron yield because you don't have your single crystal as an insulator. And so it's not feasible to do here total yield experiment, unfortunately. So we had a fluorescence experiment to do. And we got very, very nice results. And we really could show that is an angular dependent. And we were very happy about this. And then only very recently, so only a couple of weeks ago, less than a couple of weeks ago, we discussed with Frank de Groot, who is a theorist from Belgium. And he showed very clearly that he did some calculations, and he could really very, very clearly show that also the fluorescence yield already shows some angular dependence. So we have to correct our data that I'm showing and sharing you with you here, or before we can publish them for the fluorescence angular dependent yield. And this is why I'm skipping this part of the talk and finishing here. Thanking you very much for your attention. Of course, not leaving you without a future task that we are going to follow. So we have really the idea still to have a control of the intermolecular spin couplings, and we really would like in the future to manipulate our spin states. So thank you very much for your kind attention.
Okay, thank you very much. Yeah, thank you very much, Eva. Now, I want to ask one brief question. Okay, time is already 7 minutes over now, but please ask one brief question. Okay, Valentin.
Yeah, great talk. So I especially like the part where you put the molecules on the surface using electrospray. So if I'm not mistaken, if you use, say, phthalocyanine molecules on the surface, they at room temperature, they constantly running on the surface. So might be the case that this nice arrangement of molecules you observe for your crowns is also due to the fact that after deposition, the molecule run on the surface until they bump to each other and form these nice patterns?
Well, I would agree if they really would stick together, like on the gold surface that I showed you. On the gold surface, it's for sure that we had like by UHV deposition, you have a lot of amount of molecules that you put, or you can control this. So you can make sure that you have really a monolayer coverage. Then of course, it's the arrangement, I fully agree. For the electrospray deposition, we have in the first attempts at least, and also because it's really molecule expansive. So you need a lot of molecules in order to get some molecules on the surface deposited. So it's expensive in chemistry point of view. Painful for the co-workers to have to prepare huge amounts. I think the you saw the very nice arrangement relative to the kappa 01 to the kappa 100 surface. Also, if they were isolated ones, at least from the STM picture. So I don't think that they're running as long as they meet each other, but they are happy to really hybridize with the surface itself. So this gives us a good indication, at least. Of course, we cannot exclude that upon heating, they would probably gather together.
Okay, thank you very much. Okay, now thanks again, Eva. And now move to the next speakers. Thank you very much. And now next speaker is Valentin. Yeah, please.
Right. Thank you. Can you see the slide? Yeah.
Yes.
Yeah, okay, great.
Almost.
So I also would like to start with recalling one of my interactions with Kostya. Since we work on several projects, but this one is not the one we work together on, but we were going to. And last December, when we had a talk on the phone, we discovered that we are both going to participate in a big Spintronics project. And we've been quite happy, and we thought that we may collaborate on it in our usual manner. So we make the compounds, and make some measurements, and he will explain to us what we actually obtained. And during this talk, I told that I really enjoyed his paper on spin chemistry and spintronics, where he, with his co-author, explained that basically the same two fields which use just different names in different terms. And I told him that since he already explained chemistry to spintronic scientists, now he ought to write another review in which he would explain spintronics to chemists. And he laughed and said that maybe one day we have to write this review together. And we even agreed that on our next in-person meeting, we would maybe discuss it. Obviously, there was no next in-person meeting, so that project stopped without even started. But why we both thought that it might be a good idea to explain in more detail spintronics to chemists. Well, if you look at even at our abstract book of this conference, you will see that it has quite a lot of word spintronic in all these abstracts. It's here like 45 times on like each 5th page. And you would suggest that spintronic is very commonly understood field in molecular magnetism community. And sometimes it is. And there are people on this conference who do real spintronics, and you know who I'm talking about, and guys, you're amazing. But I also went to some of my colleagues who are like me, closer to synthetic part of the work. And what they said is that, well, it's just another onyx kind of science. So we're all very comfortable with electronics because we meet it every day. And then we know that there's electron, there is photon, which also finishes with on. And so there is a photonics and also somehow works. And probably spintronics is also the same kind of science, but you know, you can just take a word which finishes with on and x at the end and hope you created a new branch of science. But spintronics indeed is a branch of science, and as well as spin orbitronics, as magnonics, as excitronics, as polaronics, these all fields exist. And spintronics is probably the worst because there is no word spintron. And but we don't really care because, well, we're chemists, we're making compounds, we're not studying some real physics. But it seems that it's not that hard to at least understand the basis of spintronics, because there is a lot of things which can be done by good synthetical chemists in that field, I believe. So obviously there is not spintron, but it's spin electronics. And as I said, electronics is simple and easy to understand. And probably the major concept in spintronics, which already Effa introduced very nicely, but I'm going to run through it very shortly, is magnetoresistance. So that's probably the simplest spintronic concept. And it's an old concept. So as all good in physics, which was discovered in the 19th century, was discovered by Lord Kelvin himself. And the sign of this change of resistance in magnetic field was, and the value of its change was very, very small. So when people managed to increase it over several magnitudes of value, they obviously called it giant magnetoresistance because it was really, really big. And by this choice of terms, they determined next terms in the field, because what do you do if you already have giant magnetoresistance and then you increase it over several additional magnitudes of value? Well, you will have to choose another word. So there is a colossal magnetoresistance, and now there is even higher extraordinary magnetoresistance, although there is nothing ordinary about giant magnetoresistance actually. And probably you know that it was this discovery was awarded by Nobel Prize, and many people think that was the first applications of nanotechnology. Why nanotechnology? Because it was discovered when people learned how to make metallic films of very, very small thickness. And the first device, which probably too schematically shown here on the slide, is called spin valve. So again, it was shown several times over this conference. So in the simplest case, it's just several films, and were made of, for some reason it doesn't, oh yeah. So usually two outer layers are made of ferromagnetic metal, like iron, cobalt, and in between we have either a layer of non-magnetic metal, or it could be dielectric. And in the first case, we will talk about spin valve. In the second case, we will call it magnetic tunnel junction. And since ferromagnetic layers can be magnetized in different directions, at least in principle, we have two configurations, the parallel one, which for some reason have low resistance, and anti-parallel, which usually have high resistance. So if we make the next step and make these films out of different ferromagnetic materials, for example, cobalt and alloy of nickel and iron, and if these metals have completely different coercivity, so we can remagnetize them at different values of external magnetic field, we can do a nice thing. So we can magnetize both of these layers in the same direction and start reducing magnetic field. So and we will go to zero field, they will stay magnetized by ferromagnets after all. But when we passes through the coercive field for permalloy layer, it will get remagnetized. And so the configuration will switch to anti-parallel configuration, which has larger resistivity. And if we keep going to a negative direction of magnetic field, situations again stays the same until we reach the ferromagnetic the coercivity field for the cobalt layer, and at that moment it will get remagnetized. So again, we have parallel configuration, and again, the resistivity drops to the small value. And if you go to the opposite direction, again, it goes the same way. We have nice, completely symmetric pattern, which experimentally look, at least for me, like some kind of hair ears, sorry. And that's a very famous picture, which you can see in many, many papers on spintronics. And but it was dealing with regular inorganic spintronics. So why we would love to make spintronics molecular? Well, mostly because we are chemists and we deal with molecules, but it would be nice to go from this dry sand, which is made of totally inorganic materials, to something which is juicier, which has some organic additional layer, which can lead to some changes. There are even some works where people trying to get rid completely of metals inside and substitute these ferromagnetic layers with molecular magnets. And I know like several of work which were trying to do so. But most of the work in the field in molecular spintronics is that middle picture when people add organics in between and see how it changes the magnetic resistance or other properties. And I've already showed you this slide, the first example of molecular spin valve. But what I would like to stress here is that magnetic resistance here is switched in the other direction. So these ears over here are directed down instead of usual picture where pointing up. So magnetic resistance is negative. Anti-parallel configuration for some reason here have less resistance than the parallel configuration. And there is no simple explanation immediately why is it so. There is even more unusual things. For example, this is work from Professor Coronado group. And what they did two almost exactly the same devices with cobalt and permanently ferromagnetic electrodes, with additional tunnel and barrier of aluminum oxide, and they use molecular magnets to put inside. And devices are only different on which electrode they put this oxide layer. One device had it on cobalt, the second device had it on permalloy. And it is not such a big change, but it leads to dramatic changes in magnetic resistivity, because for cobalt, for permalloy molecular contactum, they had negative magnetic resistivity, and for cobalt to molecular magnet contact, they have a positive magnetic resistivity. So somehow the contact of molecules to the ferromagnetic surface, which just one, maybe two molecular layers, led to complete change of magnetic behavior. And there is a huge number of works in the field now which discuss why is it so. And the short description would be because of spin interface. So molecules, let's sketch a word, molecules on the surface first, or maybe two molecular layers close to a ferromagnet, hybridize with it and form some states which critically impact the spin transfer in the material. And another example from Coronado's group is the device where they use, again, molecular magnets with different lanthanides. And they showed that if you take terbium complex, which is a molecular magnet with quite high anisptropy, and if you take completely diamagnetic compound of yttrium, which are very, very close in structure, these are very similar compounds. So the magnetic resistivity is approximately the same. So they look a little bit different, but still both magnetic resistivity is positive. It's all of order of 5%. So there is not such a major difference, but you would expect that if you have paramagnetic molecule and diamagnetic molecule on the surface through which you tunnel your spins or if you travel your spins, it should somehow influence the transport. But for some reason, it didn't. And it is, again, not totally clear why it's happening. And at that moment, it got me thinking, so what would be ideal compounds to test if paramagnetic nature of a complex impacts the spin transfer? So it should be compounds, it should be a series of compounds which have absolutely same structure, absolutely same possibility to put them on the surface, but somehow different magnetic properties. And obviously they have to be semiconductors in some way so they can transport the charges and spins as well. And they need to be suitable to make a films on the surface, preferably by sublimation, because it would be probably one of the best films. And yeah, it would be also great if we could somehow switch magnetic properties so to see how magnetic properties influence against spin transport. And if you've been on this conference for several times, you probably already getting what I'm getting to. So I just love showing the picture of Clathrochelates, compounds I've been working for many years. And if you haven't seen them yet, you may think that they're quite complex looking, but in fact, these are very simple compounds to obtain. Okay. Yeah, because we had self-assembling solutions. So we take a metal ion, we put 3 portions of dioxide fragment, we self-assembly around the metal, and then we just kept them together with suitable capping fragments like boron-containing groups here. And the best part is these compounds have very diverse but very unusual magnetic properties. So depending on the metal ion structure, it could be diamagnetic, it could be spin crossover complexes, they could be high spin, they could be low spin. Some of them are really good single molecule magnets, and these compounds are really, really stable because the metal is inside this cage, it protects it, so we can get not only iron 2 or cobalt 2, but also iron 1, cobalt 1. And these compounds, in most cases, are charge compensated complexes, so we can form films from them by vacuum deposition. And the most important part is that since the metal is inside, it's the influence of the choice of metal on the structure of a compound is very small. So here we have a volume of elementary cell for 2 compounds. So this part is volume of elementary cell for iron complex, and the lower for cobalt. So iron is diamagnetic at all temperatures, and cobalt is spin transition complex. So there is a spin crossover here. And you can see that a spin crossover only slightly, very, very slightly change the volume of elementary cell. Also, people from spin crossover research know that usually you have a spin transition, you have a phase transition. So the lattice expands quite dramatically. And you may say that you still can see some difference between iron and cobalt. Yeah, that's because I blown up y-axis here. So if I put the same data here, you probably would see that these compounds are basically the same. The structure is the same, but they have completely different properties, magnetic properties. So additionally, we checked if we can make a films out of these compounds, and we've been able to make the films which still have this spin transition behavior. So we just here we have a cobalt complex, we lower temperature, and we see the change in the spectrum, which shows that spin transition is still operating. And the films are of very, very good quality. So they're really uniform and without any defects. And if we check EDX spectra of the film and compare it with the spectra of bulk sample, we'll see that with the exception of the substrate, the spectra are absolutely the same. So compounds survive vacuum deposition, they form nice layers, and it means that in principle, we could make spintronic devices out of Clathrochelates. So the main idea was, so let's make exactly the same 2 spintronic devices with different Clathrochelates of the same structure, but with iron and with cobalt. One would be diamagnetic over all temperatures, the second would be paramagnetic in all temperatures, and additionally have a spin transition. And let's measure electron and transport properties at different temperatures. So here we would have 2 possible ways how to approach this task. So we are dealing with molecular spintronics. So we can either go to people who are doing regular spintronics, and so people who are doing inorganic spintronics for some reason, yeah. Or we can start with people who are working with molecular electronics and work our way from here. So in the first case, we just need to add some molecules. So now we would have molecular spintronics. And in the second case, we would have to add some spin to convert electronics to spintronics. It seems that it's almost the same approach, but technically it's completely different way of studying and making devices, because in regular spintronics field, people usually pay a lot of attention to making really nice ferromagnetic films. They use very advanced techniques for making the ferromagnetic layers. It could be metals, but it also could be some oxides, which are also ferromagnetic. They carefully anneal each layer at specific temperature to make sure that they have exact structure, which benefits the spin transport. And here, from organic point of view, we just need to somehow add somewhere some organic layer. And the opposite way would be to go to people who are doing molecular electronics. So, for example, people who do photovoltaics, and they usually mostly working with solution state methods. So it's just drop casting, spin coating. And if we really need to make metal films, because we need something to transfer electricity, it's mostly done by thermal evaporation, which leads to not that good quality of metallic films. And obviously, the first approach probably would be better, but we are organic chemists, we are synthetics, and it was really simpler to us to find people who work in molecular electronics and ask them to make some devices together with us. So we use this approach, and now I'm starting to think that maybe it was not the right choice. So, but we still had some further choices to make. So we had to decide how we will make our device. And the simplest way would be thermal evaporation. So we just use ultra-high vacuum, we heat the sample, it could be organic compound, it could be a metal compound, and we deposit them on some surface using some masks. We had to decide what ferromagnetic materials we would use. So we decided to use cobalt and nickel with thickness of 50 nanometers. And we use it because we had it on hand. So again, we'll see that it probably was not the best choice. And so we started to make the nickel on some surface, and then we put molecular layers, our Clathrochelates complexes. Then usually on the top of the molecular layer, people in the field put additional tunneling barrier, some oxide layer. It could be aluminum, which is oxidized then in plasma. And here we decided to use vanadium oxide because, again, we had it, and because we knew what it is possible to deposit it by the same method, by this thermal evaporation in the same chamber. And finally, we finished this system with cobalt electrode. And here how this device actually look like. So it's two crossing electrodes, and we can independently connect contacts to them. And we decided that it's time to make some measurements. And we first discovered that actually the thermal evaporation is not the best choice for spintronics, that cobalt and nickel pair is not the good idea for spintronics, and vanadium oxide was extremely bad idea to use, and I will show you why it is so. So if you want to know some details, tomorrow evening during poster session, Ivan Zlobin presents his poster where he will describe it in more details, but certainly at first we decided that we have to measure the usual resistivity of these devices. So the good news was that we can clearly see with very good reproducibility that iron devices are completely different in resistivity from cobalt devices. And if we skip the molecular layer at all and just make cobalt oxide nickel device, it will have again completely different, well reproducible resistivity. So at this moment, we knew that at least we can make the device, and it's highly reproducible. And additional result, which was kind of surprising for us, that we have completely different resistivity for cobalt and the iron films. And I'm not sure why is it so. So my first guess would be that redox properties of cobalt clathrochelates and iron clathrochelates are well studied, and it is known that for same structure, cobalt would have almost 1 volt smaller reduction potential. So probably electron transport in these layers depends on the possibility of the electron to reside on the metal, and it would explain why it's easy to transfer spins or electrons across cobalt and across iron. So we had resistivity, we had resistance. Now we would love to know if we have magnetoresistance. And we haven't been able to detect magnetoresistance for any single device we made. And the possible problems that could lead to it. The first would be that tunneling junction, which was chosen to be out of vanadium oxide, first of all, it was too thick. So at first we decided that we'd use the same 10 nanometers, which maybe is not too thick, but most people in the field using tunneling junction over a couple of nanometers. So maybe it was just not possible to tunnel through. And the second, and I think that's the major problem here, is that vanadium is closer to the end of periodic table in comparison, let's say aluminum. So it has strong spin orbit coupling, so it should lead to faster spin relaxation. So maybe that was the problem. Obviously, there could be a problem that clathrochelates are not good for spintronics. So we decided to check, and we made some devices which are much simpler. They don't have anything of clathrochelates nature. They actually described in literature, or at least for very, very similar devices. And we didn't observe magnetoresistance even for devices we are supposed to have so. So obviously there was something wrong with our devices from a point of view of spintronics. So again, we don't know yet what exactly was wrong. So maybe it was a problem with ferromagnetic electrodes, because by thermal evaporations leads to kind of uncontrollable formation of structure of ferromagnetic layers. And it means that it is possible that coercivity of cobalt and nickel films could be close enough, quite close to each other, so we are just not able to remagnetize them separately. Or another possible and quite probable reason would be that at first we decided that we will try to do everything, let's say, at home, and we tried to make the measurements using just our lab grade source matter, and we did it only at room temperature at 80 kelvins. So probably what we are going to do in the future, we're going to change it to different sputtering technologies for ferromagnetic layer production. And we for sure are going to use PPMS device instead of making our own setup for magnet-resistant measurements. But it would be too sad to finish here saying that we didn't get any meaningful result. So to show you what I still think that Clathrochelates are suitable for molecular spintronics and for that matter for molecular electronics as well, I also want to show you another result which was made with the same Clathrochelates, this time in so-called transistor geometry. So we started with a substrate and we added another electrode. So it's gate and electrode, and when it's covered with aluminum oxide, it's isolated. So that's general organic field effect transistor geometry. When we use Clathrochelate level, we added at first it was not clear for me why we added it. So people from molecular electronics community who've been working with said that it's better to have fullerene in device, so I believed it. So we added fullerene on the top to assist with electron transfer, and on the top of it we added two more electrodes, which are source and drain. So by general transistors, and we, actually not we, but we applied the voltage on gate electrode and checked how the current through between source and drain passes. And originally it was, at first it was very usual picture for organic transistors like here. So it's regular transistor curve. So the higher the voltage on a gate, the bigger the current passes through source and drain. But what was unusual is that if we applied additional potential on a gate and at the same time add light, somehow it led to injection of electrons towards a Clathrochelate layer, and transistor curve shifted very strongly to the left for over 4 volts. Or it means that the current through drain to source increased by approximately 4 orders of magnitude. So we switched from off state of transistor to on state of transistor. And what is more important, when it was switched, it stays so for at least a full day. So we didn't check if it works longer, but you can see that when we started in off state and switched it to on state, it stays for 60,000 seconds. It's like 16 hours. So that's pretty good behavior. So we do have device which can be switched by external field and light, and most important, switched back if we want to. So if I see that results, if I saw that results a year ago, I would immediately say, wow, great, let's substitute source and drain electrodes with something ferromagnetic, and then we'll have a spin transistor or something. Now I'm not that sure that it would work. So we tried to make Spintronics devices, we failed so far, but I still think that it is possible. So it turned out that molecular spintronics is not that easy thing to do. So 1 year ago, I thought that it would be quite simple if we have good compounds. But I still think that, especially if people from spintronic communities who know what they're doing, who know how to make devices, would decide to join forces, it would be great to see if indeed collaboration between physicists and chemists can lead to some progress in molecular spintronics. So these are people who did all of the job. And I remind you that if you want to know more details, tomorrow evening there will be poster P27. And thank you for your attention.
Thank you very much. Okay, now open for the discussion. Any question? Any question or comment? Okay, Nikolai.
Dear Valentin, I every time enjoy your presentation and information which you gave all of us about field of your research. Valentin, and I have a question about C60 layers in optical devices. which thick is it?
Sorry, the question was?
How thick is the C60 layer in this device?
Okay, yeah. In that device, it's of the order of 50 nanometers, approximately the same thickness as for Clathrochelates.
And is it enough to irradiate by light, or yes, this light?
Yeah, well, it is thin enough. It is thin enough, so that part is you can see through it actually. So the metal parts are reflecting, but the organic part is basically it's quite optically transmissible. So I think that photons go to Clathrochelates as well, but again, it is very far from my field, and I don't really understand what's going on in transistors. So I'm trying to, but so far I'm not sure.
Thank you very much for your.
Okay, thank you very much. Okay, thanks again to Valentin again, and now move to the next speakers. Next speaker is Gerd Buntkowsky. Please.
Okay, so I try to share my screen, and okay, can you see it?
Yes.
Okay, so of course, first I would like to thank the organizers for inviting me here, and of course it's a special honor to be in a session which is devoted to Kostya. And this shows us in a better time. About 2 years ago, no COVID, everything was fine. I was visiting the Institute in Novosibirsk. And during this time, I think nobody could really imagine what's going on. And the history between Kostya and me goes back nearly 20 years. I know him still when he was a PhD student in Berlin in the physics department. During this time, I had just finished my habilitation in chemistry. And then we started to get into contact. And about 10 years later, we also started to collaborate. And we have about 10 joint papers and common project. And now, okay, our main collaborations were always devoted towards hyperpolarization, and in particular towards parahydrogen-induced polarization. So I'm going to show you some of these works and to give you some ideas what we did together. Okay, the basic principle of NMR was already discussed, for example, today. And the thing is, NMR is just Chernobyl insensitive. So when you have 20,000 spins, protons, which are more sensitive normal NMR nuclei, and a field of 7 Tesla, then about 9,999 spins on the upper level, 10,001 on the lower level. And unfortunately, you're doing NMR only with this very tiny difference of 2 spins. All the rest is wasted. So all the pure chemists, they produce huge amounts of substance that we can use 0.1% of this substance for our spectroscopy. And as Daniel, for example, explained today, there are not many numbers where you can play. You can change the sample size, you can increase the magnetic field, you can lower the temperature, but this doesn't change too much. And now our idea is to use special techniques, so-called hyperpolarization techniques, which strongly increase the NMR signal. For example, that we can look at binding sites in a protein, like with a flashlight, or also in MRIs that, for example, you could look in the brain, follow some kinetics there. And to do this, you need to have techniques which increase the NMR signal. And we're using 2 of these techniques, DMP and parahydrogen-induced polarization. And today I'm talking about FIP, parahydrogen-induced polarization, because this was also where the collaboration with Kostya and the Novosibirsk Institute was strongest, or is strongest. Okay, so basically just let's remember what is parahydrogen. Parahydrogen is one of the spin isotopomers of molecular hydrogen. There are 2 of them, the parahydrogen, the autohydrogen. And the important thing is, since protons are spin 1/2 particles, the overall wave function has to be antisymmetric. Now, at normal temperatures, we're always in the lowest vibrational state, so they're always symmetric. And you can make the antisymmetry either via the rotational or with a nuclear function. And so in principle, if we have an antisymmetric spin state, we're calling it parahydrogen. If it's symmetric, we're calling it autohydrogen. And these are just some information about it. The rotational wave function for the Parahydrogen is symmetric. It has quanta J0 to 4. For autohydrogen is antisymmetric. And these are the lowest state. For the Parahydrogen, it's J equals 0 and I equals 0. And for the autohydrogen, it's J equals 1 and I equals 1. Okay, now the interesting thing is that there's an energy splitting between the singlet and the triplet state. So this is just a sketch of the singlet state. These are three triplet states. And this energy splitting is relatively large. If you look into any standard textbook in physical chemistry and calculate the numbers, you find it's about 4 times 10 to the 12 hertz. Or in other words, you have an energy splitting between spin levels, which is about corresponds to a magnetic field of nearly 90,000 Tesla. And of course, when you have a higher field, as you have seen before, you're going to get higher polarizations. So the possible maximum enhancement at typical fields of 11 Tesla is about 7,600-fold, which you can get by FIP. For the highest accessible fields, it's about 3,500. So it's really dramatic. It's nearly 1 order bigger than what you can get, for example, with DNP. And the other thing is Parahydrogen is quite inexpensive to produce because you can just convert it by putting it to lower temperatures and put in some suitable catalysts. This just shows you the Parahydrogen concentration as a function of the temperature and equilibrium. The green line here means the line temperature of liquid nitrogen. When you cool it there, you will get about an enrichment to 50-50. When you go to even lower temperatures, about 20 K, you can nearly 100% Parahydrogen. And with this, you can do these experiments. Okay. So our first experiments, we did a bit like Tom Cruise in this old movie. We just checked it, just put everything in the spectrometer and look for the signals. Of course, this is not too reproducible for this reason. What we did later was we built some kind of automatic FIP, like a kind of automatic reactor, where everything is controlled by the NMR spectrometer, and which gives a much better reproducibility. And these were the people who were mainly involved in construction setup. It was Gerd Sauer, Alexei Kyutin, and Stefan Knecht, who worked in the different iterations of the our FIP spectrometer. And most of this work was done in close collaboration with the ITC Institute, especially with Alexandra Yogoskaya and also with Kostya Ivanov. This here gives you an idea about how everything works in principle. So you see we have electronic valves. All the electronic valves are controlled by the NMR spectrometer. With this, for example, we can flush the NMR tube. We can put the Parahydrogen inside. We can quench the reaction by flushing it again with an inert gas. And everything basically then is controlled by the NMR spectrometer. So this is a bit more practical kind of view. You see it looks relatively fancy. And the nice thing is also since about 2 years or so, we have a Parahydrogen generator. It's from Advanced Research Systems. It's about 50K euro and delivers 95% enriched Parahydrogen. It's very, very stable and easy to use, much better than any other vendor. Okay, now this is just some photos of the setup. Here basically uses electronic valves. Here's the NMR magnet of the normal spectrometer. These here are the control valves with the magnetic valves. And just some short ups. And now just let's look how the experiment is working. So on the first step, we just put our substrate in normal NMR tube. Place the NMR tube inside of the spectrometer. Then inside of the spectrometer, we can start measuring the first spectrum, which is just before any reaction has taken place. Then we bubble Parahydrogen through it. Once more measures the spectra, then you see these very strong antiphase signals, which are characteristic for the FIP effect. So for comparison, this is 16 scans. It's just a single scan with FIP. So you see it's already here a strong enhancement. And afterwards, we measure one more the relaxed spectrum to see how much product we have formed. And you see in the relaxed spectrum, you see basically nothing here. So only very tiny amount of the substrate was consumed during the hydrogenation reaction, which occurs here. And this is just to show you a bit how good the reproducibility of our setup is. We have better than 1 or 2% of reproducibility. So we really can use this, for example, for measuring kinetic curves. In this case, it was just a simple experiment to just look for the dissolution kinetics of the hydrogen inside of the solvents. And if you want some details about this setup, you can read in this manuscript from Alexei and us. Okay, now we have this nice toy to play around. Let's see what we can do with it. And we're mainly interested in the enhancement of biomolecules. So what we're doing is we're putting some unsaturated group inside of a biomolecule. We make a hydrogenation with parahydrogen. Afterwards, we get the hyperpolarized product. And this is what we are detecting with this kind of experiments. And this here is a bit the so-called vision. So finally, you want to use this kind of molecules, for example, to bind them to a protein and look selectively to the binding site. But this is still a long way to go. At the moment, we're still playing with the biomolecules. Okay, now what you need for the hydrogenation is an unsaturated group. And we wanted to use peptides, and we thought, okay, we don't want to have any unsaturated groups in the backbones because it might disturb the conformation of the molecule. So for this reason, we decided we focus on side chains. And the easiest unsaturated group you can put in a side chain is a propagyl group, like shown here. Okay, and propagyl has a nice thing because it's a triple bond. You can do 2 hydrogenations. So basically, there should be 2 products here where you could get a Fib result. Okay, and so when we started playing around with kind of things about 10 years ago, a bit more, so we were quite successful. We found could synthesize the molecules, and we found some enhancement factors of 20 or 10, which is not really something which is too big, but at least it was a nice starting point. And then we also started to use these as building blocks for standard peptide synthesis and put them into some small test peptides, some tree peptides. And also there we got these nice enhancement factors, something on the order of 10. So basically this told us in principle our idea is working. Okay, and this then was our first paper there, 2013, where we showed that we can do this kind of experiments also with a bit larger peptides. Okay, so then we thought, okay, can we also do this with some peptides which are of real biochemical use? And so we started a collaboration with the Colmar group with this molecule. It's called SFTI, sunflower trypsin inhibitor number 1. Basically, it's an enzyme inhibitor for trypsin, but it's also for matritase. Matritase is one of the things which is connected to colon cancer. So it's interesting for drug design. Okay, and so we started, put our nice propagyl glycine label inside, and we started to measure, and we didn't get any Fib. Disappointing. With the small peptides it worked, with the real one didn't work. Okay, then we asked, okay, what's going on there? In principle, there are 2 possible explanations which immediately come to your mind. Either there's a poisoning of the catalyst by the peptide, which would be really bad, or there's a blocking of the catalyst by the peptide, so it cannot come to the triple bond and hydrogenate it. In order to test this, we thought, okay, what's another possible non-natural amino acid which we can use as a triple bond is farther away from the peptide, so in order to avoid any blocking effects. And for this, we used the propagyl tyrosine. And first we tested it as a native amino acid. These are just the protection groups here. And you see basically for the native amino acids in both cases with a bit better setups than our first experiments, we got enhancement factors on the order of about 200. So both native amino acids work quite well. So let's check now when we put the propagyl tyrosine inside of the peptide. And there we see really it works much better than the glycine. Here it was enhancement factors of 15. Here still enhancement factors of more than 200. So really, this is the way to go. We have to get the triple bond more far away from the backbone. By the way, this is already the polarization about 2% of the protons. Okay, so now we use our spin label and insert it here in the SFTI chain. And then we did once more the experiments, and also in the SFTI chain, we still found enhancement factors about 70. And a factor of 17 enhancement means about a factor of 5,000 measurement time. So this was quite a nice result, which is then published in 2014. Okay. And then we started mainly the collaborations then with Alexei Koyutin to optimize our setup. And so finally, after this optimization procedure, we increased our enhancement factors to something on the order of about 1,200. 1,200 means polarizations of about 10% of the protons. Or in other words, we have enhancement factors which are big enough to reduce the measurement time by a factor of 1 million. So we can do an experiment in 1 second, which otherwise would take about a week. Okay, and this is then compared to the previous one as of 40. Okay, now, okay, with these large enhancement factors, we got the idea. In principle, there are techniques where you can measure a 2D NMR spectra in a single shot. These techniques are called ultra-fast 2D NMR. Ultra-fast 2D NMR works when you have very large signals. Is it possible to combine ultra-fast 2D NMR with FIP and do something like a single scan detection of 2D NMR spectra? So this is just basically for those who don't know the techniques. This is a very nice review by Lucio Friedman and Patrick Jourado, who explains how ultra-fast 2D NMR is working. In principle, it's a technique which is related also to tomography. So you're applying an NMR gradient on your sample. By this gradient, you have different slices, and each of these slices more or less corresponds to the normal T1 step in the normal 2D NMR experiment. So with this, basically, you can do the whole TT experiment in a single shot. Okay, this was a pulse sequence which then Alexei Koyutin implemented for doing these experiments. And in first, it worked. So these are some of the first spectra we got. For example, this is an ultra-fast PIP COSI, this is an ultra-fast PIP TOXI. So both are basically single scan 2D NMR spectra. And in contrast, for the thermal spectra, to get a similar signal to noise, we would need about half an hour of measurement time. Okay, this was quite successful. Then Gerd started to optimize it and check how low can we go with concentrations and still get a single shot 2D NMR spectra. So this is just our references from before. And now we just, sorry, this was 60 millimolar. So let's go down 1 millimolar, still works fine. Let's go to 500 micromolar, still works fine. Let's go to 300 micromolar, still works fine. So really we can get micromolar resolution to the NMR spectra and single shot with FIP. And so this here just shows this, and in principle, so its technique really works, and you can go to relatively low concentrations and still get this spectra very fast. Okay, and then we made this very nice paper, which was together with Kostia. And one of Kostia's collaborators made this very nice graphics here to symbolize it. So how the clock is running only a very short time and we're doing this kind of 2D experiments. Okay, now, very recently we had started another collaboration with Kostia. And actually, this collaboration was an outcome of a visit in Novosibirsk. I was there together with Stefan Knecht. Kostia was there because he had joined a DFG RSF proposal, and also James Iles was there as a guest during this time. And as usual, the important thing of conference is not what you're speaking, but afterwards what you're discussing during a beer. And during the beer, we got the idea to combine FIP with the detection of one of the substrates in this citric acid cycle. So when you look at the citric acid cycle, you see one of the steps here is when you come to the fumarate, which is a double bond, to the malate, which is a single bond. So basically it's a hydrogenation. So we discussed whether it would be possible then to do an experiment and detect this hydrogenation step by FIP, because this would really be something which is quite interesting. So because this is one of the markers, for example, for some of the drugs against cancer, this step here is a marker for seeing whether these drugs are efficient or not. Okay, so here it's a bit more detail. And to do the experiment, we did it in 2 steps. We checked with the fumarate in the first hydrogenation step by going from acetylene decarboxylate to fumarate, and then a second one from fumarate to succinate. We wanted to see whether we can follow these steps by FIP. And in fact, it worked. And it worked so good that basically it was even possible to detect it in the MRI and not only in the NMR. So these are phantom MRIs. So where you see basically the signal as a hyperpolarized signal, also how it decays, the fumarate. So in fact, we really can use FIP hyperpolarization in principle for doing the MRT detection, and then in the long run, perhaps also using it in diagnostics to follow, for example, how the pharmacokinetics of such a thing works. And if you want to know a bit more about this, so there's a paper by James, Stefan, the first one. Also, we have many collaborators. Kostya was very important. I told you we got the idea when we were visiting him. And then there's a follow-up paper then where also basically then James and Stefan mainly developed it a way for purifying as a substrate by just falling it out of solution, afterwards resolving it, and in principle then the hyperpolarization is still conserved. And then Laura recently did some studies where she looked at the reaction kinetics, how to optimize it and to get the highest amount of hyperpolarized fumarate for this diagnostics. And with these 3 papers, you can get some extra information about it. And finally, at the end, I will show you more collaboration with Kostya, which is a bit more hardcore physical chemistry and spin dynamics. And the whole thing started about 5 years ago or so. During this time, Gerd was measuring FIP experiments, and Gerd was a very observant student. So she realized that the line of the free dissolved hydrogen in the solution NMR spectra always looked funny. And she also found out it looks only funny when you put in fresh parahydrogen inside. When the parahydrogen has converted to normal oil hydrogen, after some time it disappears. So this is just shows the hydrogen line for different times. You see initially there is this phase distortions here. That's what I mean with looking funny. And this phase distortions get weaker, disappear after some time. Okay. Now, of course, the obvious question was, is it bad phasing? But all the other lines in the spectra look nice, so it could not be bad phasing. It must be some real effect. And then we started to thinking about it. And the first thing what you need to do when you think about this is also what everybody in botany does. Just give it first a name that you know what you were talking about. And so we created the very creative name partial negative line, because obviously so what you have, partial negative line. Okay, but this doesn't answer what was the origin of the PNL. And by the way, similar things were observed more or less at the same time also by Igor Goptyuk. And then, okay, we did some experiments, and these experiments showed us that basically the PNL is a 2-spin process. 2-spin process you can show, for example, by nutation experiments, because in the nutation explosion, the nutation frequency is twice the IP1 and not 1 times like normal nutation. Or you can do something which is called opposite detection. Opposite detection is an experiment which was developed by Duckett about 10 years ago, which just filters out the 2-spin part from the single spin covariances out of the NMR. And both proved that it's really a 2-spin process. And then we started scratching our head, what could be going on. Fortunately, then Kostya stops the scratching of our head, because he then was able to show what's going on. And then he made a model which is roughly shown like here. So initially you start with a parahydrogen. Now, in the solution, you have the hydrogen and you also have the catalyst present. And this means basically there are bound states, intermediates more precisely, where the catalyst and the parahydrogen are bound to each other. And the result of this binding is that auto-para conversions between the S0 and the T0 state become possible. So in other words, what the catalyst does, it converts part of the singlets population S0 to the T0 population. And afterwards, when the molecule then goes back into solution, we have then overpopulation of the T0 state. And this overpopulation of the T0 state basically is what gives us this partial negative line, because the NMR line of the dissolved hydrogen is thus the signal which you get from the auto hydrogen. Parahydrogen is NMR dead, it is NMR silent. Okay, and then I wrote a program to simulate this model, and we really could show quantitatively also that it works. And we got this nice formula for this splitting, which you see as the antiphase signal. And then we thought, yeah, okay, but if this is the case, then there also must be some intermediate. So we measured the spectra. So we measured it both in Darmstadt and in Novosibirsk and different fields, and we didn't find anything, no intermediate. We were a bit restricted with the number of scans because it's just the lifetime of the catalyst. After this time, the catalyst is just dead. So there was nothing. Okay, so what can you do if you find something not direct? You have to do it indirectly. So then what we did was a kind of experiment, which is a bit similar to the CEST technique. We call it panel, partial negative line experiment. What you're doing is you're irradiating a soft, long RF pulse and sweep the soft, long RF pulse through the spectrum, and then the effect is more or less similar like CEST. When you hit a resonance, you can transfer this resonance to another spin if they are coupled via exchange. In our case, the intermediate and the free hydrogen lanes are coupled by exchange. So we said, let's check whether we can use this for detecting this intermediate. And in effect, it was very successful. So basically, what you're seeing here is experiments. Here below are some simulations of it. And you see basically we really have some intermediates here in the regime about minus 15 ppm, so typical hydride region, which shows by this indirect technique, we really can detect a catalyst which is otherwise invisible. And we have estimated that this experiment is about a factor of 1,000 times more sensitive for detection of intermediates than normal NMR. Okay, and if you want to read a bit more about this, you can find it basically in this paper, which is from Kostya, myself, and the rest of our collaborations there. Okay, with this I'm also at the end of my talk, and I've shown you a bit how we can detect intermediates very sensitive. I've shown you how we can have FIP experiments done very reproducible, how you can apply it to biomolecules, in particular to peptides, how you can use it for the detection of biomarkers. And these are the people from my group, which are mainly involved. Is basically Laura Wienans, Franziska Theis, Jonas Linz, Julia Milos-Lawine, and Jan Kergesner. They are my current FIP group in Darmstadt. The other ones I've already shown you on the slides. The money is mainly from the DFG and some local funding sources. And finally, okay, once more, I want to thank Kostya for this great collaboration for 10 years and for being a good friend for 20 years. And as some of you perhaps know, in a bit less than 2 weeks, there's another conference which is also dedicated to Kostya. It's the Icon 3 conference. Daniel already talked a bit about it because Kostya was basically the spiritus mentor for creating this meeting, which is now organized by Daniel, Madhu, and myself. And we have decided that we have one day where we have talks also devoted to the work of Kostya. And with this, thank you for your attention.
Thank you very much. Oh, hyperpolarized. Anyway, thank you very much. Now open for discussion. Any question or comment? Okay, I have only one comment. But you mentioned about some how to say flip angle dependence of some polarization pattern, right?
Yeah.
I wonder, is it similar with that was observed in the kidnap multiplet effect?
Okay, most probably. I'm not so 100% familiar with the kidnap multi, but basically, most probably it's the same idea. In principle, when you have two-spin order, suppose, for example, both spins are pointing upwards. When doing a 180-degree pulse, both spins point downwards, and the dipole interaction or J coupling has not changed. So basically, for having something like a 90-degree pulse normal NMR, you need to do a 45-degree in two-spin order.
Okay. Okay. Thank you very much.
Welcome.
Okay. Any other question? If not, okay. Now I close this session. this morning session anyway. Okay, thank you very much. Okay, now now pass to the Matvey, please.
Dear speakers of all this morning session, many thanks to you. I would like to make a very brief announcement. So we are a little bit behind the schedule, so we suggest that now we make a break for 20 minutes, and then we start the next session at 15:20 Moscow time. Yeah, and good news, well, not exactly good news, but anyway, we have one cancellation in the afternoon session, so we will slowly get back on the track, and we will finish on time. So please get back in 20 minutes and we will continue with the afternoon session. Thank you very much.
Thank you very much.
Matvey?